Let's get the solution to this problem about the ice cube floating on the surface of water. Ice is just a little bit less dense than water. It's a very interesting property that probably Gch10 makes a comment about. It's really useful, especially to animals that live in the water, fish, that the fact that ice is less dense than water means that all the freezing occurs on the surface of a lake, and that prevents the warmer water from circulating up to the surface and freezing so fast. And that means that, small lakes or ponds that freeze solid all the way through, your fish can't survive in there. But because ice floats on the surface, it tends to insulate the water down below. If ice were heavier than water, more dense, the ice would sink and then new ice would form and the whole thing would eventually freeze on cold days. But it's harder to freeze a big body of water because ice floats. And it's sort of counterintuitive. Most things get more dense when they turn from liquid to solid, but water is just sort of backwards in that sense. When you freeze it, you would think that the water molecules would get a little bit closer together as they form into a lattice, but they actually have to spread apart to get into a lattice. Very interesting, but useful too. Okay, we want to figure out how far the ice cube sticks out of the water. This is a difficult problem if you've never seen an example, so if you didn't get far on it, that's not surprising. So let's do it together. When it's floating like this, it's in equilibrium. It's not going up or down, and so the forces have to balance. What force is going up? The buoyant force. What force is going down? The weight force from the ice cube. Earth is pulling down on it with its mass. So how do I calculate the weight of the ice cube? Well, I multiplied the density of ice times the volume of ice, that's the mass of the ice, and then multiply by little g, that's the weight of the ice. So in this case, putting in for the volume and the density that was given, that gives me the weight is 0.1404 newtons. That's the weight of the ice cube. And since the ice cube's in equilibrium, it's just happily floating there, the buoyant force must be equal to that weight force. Okay? So, what I want to do is figure out what this distance is that the ice cube sticks above water. So I'm going to draw a little diagram here, a side view of the ice cube floating in the water. And let's assume that a distance x floats above the water. Of course, the full height of it is 2.5 centimeters, so that's 0.025 meters here. And I'm going to use Archimedes' principle, okay? The weight in this case, the buoyant force, I can see, the buoyant force is 0.1404 newtons, okay? So the buoyant force is that, but I also know that that's equal to the weight of the water pushed out of the way. And when I do that, I only need to calculate the weight of the water that would fit into this bottom part, the part of the ice cube that's submerged. That's the only weight, the only water that is displaced. The top of the ice cube isn't displacing any water. That's the meaning of displaced here. So let's write that in terms of x. The weight of the water displaced is the density of water times the volume of the water that's pushed out of the way. So what is that? Well, the area of the bottom is 0.025 times 0.025, and the height of this side that fits under the water is 0.025 minus x. That's just the height that's underneath the water. So the volume of the water is displaced times rho gives me the mass of the water displaced, times little g gives me the weight of the water displaced, and the volume of the water displaced, by what I just said, was 0.025 minus x, that's the height that fits under the water, times each of the, the linear dimensions on the bottom is 0.025, so I get an additional 0.025 squared. Density of water is 1,000, little g is 9.8, and all of that is equal to the buoyant force, which from this free body diagram is 0.01404 newtons. I can then solve this for x by dividing out all the stuff over here and just solving for x, and you get x equals 0.00208 meters or 2.1 millimeters, which, at least it doesn't obviously disagree with your intuition. When I put an ice cube in the water, most of it is below the water's surface. That's the same thing that happens with icebergs in the ocean, right? You see a little bit of ice above the surface, but most of the ice is down below. So here it's 2.5 centimeters, but a little less than 1/10 of that sticks above the surface of the water. Okay, I may have already said this here, but what determines if an object floats is how the weight compares to the buoyant force, the weight of the object compared to the buoyant force on the object. And if the object's density equals water, then it would be neutrally buoyant. It wouldn't feel a force up or down if you submerge it in water. If it's slightly less dense than water, then the buoyant force is going to be greater than that of the weight force, and it's going to go up. So what determines whether it floats or sinks is the density. If the density is less than water, it floats upward until it gets to the surface, and then the buoyant force gets less and less and less until it just balances the weight force. It rises until it's partially out of the water. If the density is greater than water, then it just keeps sinking till it hits the bottom. Oops. Next problem. You can just stop the video to work on this one. I don't think I put in a break here. But we've got a cube of aluminum of density 2,700 kilograms per cubic meter, which is 2.5 centimeters on each side, and it's connected by a light thread to a scale, one of those scales that you weigh fish on or whatever, and the scale reads in newtons, and we want to know what the scale reads when it's just hanging like this as normal, right? So we're just holding on to it, and the cube is down below. And then more interesting for our purposes is if we then submerge the cube in water, completely submerge, how does the scale reading change? What's the new scale reading? So if you want, try to figure out what both of those are. You can pause the video and then come back in just a second to see the solution. All right, so in order to do both of these, we're going to do free body diagrams. And it's always, as always for a free body diagram, it's crucial to sort of get the right body to do the free body diagram for, but here there's not too many choices. The cube is certainly in equilibrium, it's not going anywhere, and therefore the scale force balances out the weight force of the cube. And so if in terms of F net y equals 0, that would be F scale minus mg equals 0, and therefore F scale equals mg. Well, I've got to calculate that in terms of what's given here. I wasn't given m, but I know the density and I know the side length, so I can figure out what the volume is. So again, we're seeing rho Vg appearing here, but that's the same thing as mg. It just looks a little bit unfamiliar to us. So V is 0.025 times 0.025 times 0.025, right? 0.025 cubed. Rho is our 2,700, and little g is 9.8. That will give us the weight of this, which by our free body diagram, that's what the scale should read. All right, second part. Now the cube is dipped in water. The scale reading actually changes, right? In the same way that, if you were hanging by a cable, the cable would have to pull up a lot to hold you up. But then if you got dunked in water, you wouldn't feel as heavy and the cable doesn't have to pull up as much on you. So that scale reading would change. Same way here. Oh, sorry, I didn't put in the numbers up there. I forgot to click forward. The rho for aluminum, the volume calculated in terms of the cube of the edge length, and little g. So that ends up being 0.413 newtons. All right. So when we submerge it in water, again, this cube is in equilibrium. And so I'm going to do a new free body diagram, except I don't have just two forces acting on it. Now I've got three forces because I have the buoyant force from the fluid. Technically, there is a tiny buoyant force in this case. I mean, we are in the atmosphere fluid here, but the pressure hardly changes at all in the atmosphere between the top and the bottom of the cube. That's not true when you're in a dense fluid. So in this case, it really makes a difference. So in this case, we still have the weight force, we still have the scale force, but we have an additional buoyant force up. And again, it's in equilibrium. It's not going anywhere, so these forces have to balance. But since we have the additional buoyant force, the scale force doesn't have to be as big, so we expect the scale force to go down. Let's see what it is by writing the sum of the force y components equals 0. Two come in with plus signs, one comes in with a minus sign. And we're going to solve for the scale force. That's all we need to do is calculate the difference between the weight of the cube and the buoyant force. To calculate, well, the weight of the cube we already figured out earlier up here. The weight of the cube was part of what went into the scale force up there, so that's still 0.413 newtons. But now the buoyant force I'm going to calculate by the buoyant force is equal to the weight of the water displaced. What would be the weight of water that fits inside this cube? That's the volume of the cube, 0.025 cubed, times the density of water, not aluminum, because we're talking about the weight of the water displaced, so I need to use the density of water. That would be the mass of the water displaced in these parts, times little g gives me the weight of the water displaced. So you got to be careful there. Sometimes people just calculate the mass of the water displaced. That's not what Archimedes' principle says. So you put all that together and subtract it off of this, I get 0.26 newtons. So the scale reading actually goes down as we submerge this in water. Most people don't have good intuition about that, but you know about that from going in the pool, at least. Things feel lighter heavy things feel lighter when you submerge them in water. Let's do something now that tells us about the flow of fluid inside an enclosed kind of tube that you're pumping it down. Maybe this is water flowing through a tube, maybe it is air. And we're going to use something called the continuity equation, which says something that hopefully makes some sense to you. The rate at which mass is, so I'm imagining water or air going down this tube, and the tube narrows as it goes down there. The rate at which mass passes this location right here better be the same as which mass passes this location here. Why is that? Because if mass is going into this surface at a greater rate than it's coming out at this surface, then there would be mass increasing in this volume as time goes on, and something catastrophic would happen really quickly, right? If mass is building up in here, that's not the way fluid normally flows. Similarly, if mass were coming in less rapidly than it is leaving over here, then the mass would be getting less and less in here as time goes on. But when fluid is flowing in equilibrium like this, right, it's just sort of flowing and nothing's changing as time goes on other than the movement of the fluid, the mass in a certain volume isn't changing as time goes on. So that's expressed in the continuity equation, which says the rate at which mass passes. We're going to have to write that down mathematically now. The mass flow rate, the rate at which mass is passing a surface, say here at location 1, is the amount of mass that passes by it, we'll call that delta m, divided by the elapsed time, we'll call that delta t. Okay? And so we're going to assert that that's the same for this big surface area as it is for this small surface area. Okay? So that in this case, the flow rate in is the mass that goes through it, this surface, in a given amount of time divided by that time. And that should be equal to the amount of mass that flows through this surface here, divided by maybe the same amount of time. Now, we're going to analyze this for the case of an incompressible fluid. In other words, if you take air or some other gas, it might be that when you force it through at high velocities through here, that the fluid actually compresses as it goes through the tube. But that's not going to be true, or it's true to a very good approximation that water doesn't do that. Water's fairly incompressible in the way it flows. So we're going to assume that the density of the fluid is the same all the way through the tube. So there's only one rho to talk about for the fluid. So in this case, we're going to write down the fact that this at position 1 equals the same thing at position 2. And we're going to calculate the mass that flows through as, in that certain amount of time, the density of the fluid times the volume that moved through it. So here we could envision that as a cylindrical volume. Here there's a different cylinder. This cylinder has a smaller cross-section, but maybe it's longer, right? And we'll call the lengths or the heights of those cylinders delta x1 and delta x2. So the rho times the v at 1 is equal to the rho times v at 2, and therefore the v's must be the same. The delta t's are the same. We're going to calculate those v's using the geometry of it, right? The volume here is going to be A1 times delta x1, and the volume here I'm going to calculate as A2 times delta x2. So I've made those replacements here for V1 and V2. V1 and V2 are the same. And then when we follow this through, we can cancel some things out. And again, we're assuming the rho is the same all the way through. So when we cancel out the rho and cancel out the delta t, I'm sorry, don't cancel out the delta t, cancel the rho, and then use the fact that delta x1 over delta t, that's how far the fluid moved in a certain amount of time, divided by that time. That's just the rate at which the fluid is moving there. In other words, the velocity at point 1, versus the velocity at point 2. So the continuity equation, re-envisioned in this case, says for an incompressible fluid, the area, cross-sectional area times the fluid flow velocity at one region is equal to the cross-sectional area times the fluid flow velocity at another region. And whenever the cross-sectional area goes down, the fluid flow rate must go up. That kind of makes sense, right? If I'm pumping a certain amount of fluid through here, if the size of the tube gets smaller, the fluid's going to have to flow through at a greater rate to be moving at the same rate as it was over here in terms of mass flowing through. Okay, let's go on to a worksheet problem, and I think this is the last thing in this chapter. Here we've got a syringe. It's a glass cylinder of inner diameter 1 centimeter. So the inside, where the plunger is inside here, has a diameter of 1 centimeter. It's got a needle of inner diameter, 0.5 millimeter. If the plunger is pushed into the cylinder at a speed of 1 millimeter per second, so we push this down at 1 millimeter per second, with what speed does the fluid exit the needle? Okay, so try that yourself, see if you can use the continuity equation, the A1V1 equals A2V2, to figure it out, and then come back for the solution. All right, here's the solution. We're writing down that version of the continuity equation for an incompressible fluid. And in this case, we're just going to put in the numbers that were there. We got to remember the numbers that were given for the inner diameters are diameters. So if I want to change it to a radius, I take the diameter of the part where the plunger is, right? The diameter of 1 centimeter, divide by 2 to get the radius, and then pi r squared gives me the cross-sectional area of the inside there, times the speed with which the fluid is moving in this part. That should be equal to the same thing in the needle over here. So that's pi times its radius squared times the unknown v, and we're going to solve for v. And when we do that, we get 0.4 meters per second, which, putting it in the same units as it was given over here, we're pushing down at 0.5 millimeter per second. I'm sorry, we're pushing down at 1 millimeter per second. Down here in the needle, it's flowing at 400 millimeters per second, or 40 centimeters per second. So that's a really fast flow rate out of the needle of the syringe. And that is the end of chapter 10.